we add too much the aggregates?
No, what is the cementing factor based on? When you do that calculation, what are you looking at? The yield, right?
Yeah, yield.
So that tells you then, if you're under, that tells you your yield is what? Above or below the 0.1? Above, high, right? Okay, because you're technically batching more volume, but you're only putting in cement based on 0.1, right? So if your volume is greater, your unit
Yeah,
mass,
we're 0.100764, so we're over the 0.1.
Yeah.
Yeah, okay.
Just take it to 3 decimal places. So you'd be 0.101. Yeah. Okay. Yeah. So that's why. So this is the things you would find out in the lab, and then you say, okay, we gotta submit our mix design to the city of Winnipeg. We obviously we're under yielding or over yielding. We got to adjust our proportions on the 1 cubic meter basis. The 0.1 is just a working volume. Typically, if we were in Carsey, you would be batching 0.07 because 0.1, believe it or not, was way too much concrete for us when we were actually batching. The mixer was almost overflowing. But I mean, this is just a virtual lab, so I figured, 0.1 is a nice, easy number to work with, 1/10 of a cubic meter. So everything should be straightforward. Then you would give the client, this is what the trial batches all tell you about it. That's why it's called the trial batch. You're doing a trial of your mix design, and you want to make sure your mix design meets all the criteria. Okay. Capiche? Rozumiesz? Versteh?
Yeah, that's good. Thanks.
Okay. Anything else?
I think we're good.
One general comment, and you guys are probably getting a little upset with me when I was sending back emails saying your total mass isn't right. Your total mass isn't right. Or this isn't right. The amount of water that gets absorbed, what we refer to as adjusted water, that goes into the aggregates, right? So if your aggregates were bone dry, they're bone dry. If your aggregates are dry on the surface, let's say, like an SSD, and the pores are filled with water, is an SSD mass greater than an oven dry mass? Anybody?
Yes.
Yes. So that's why when you're doing your total mass on that little spreadsheet back in lab 3, is you have to include the absorbed water. It doesn't affect the volume because it's in the aggregate. If you had surface water sitting on the aggregates, then that would contribute to the volume. But because it's absorbed, okay, you're only calculating the absorbed mass. It still adds weight to all your other ingredients. So you have to include that in your total mass of concrete. Okay, so you would total the 184 to 33 or 29 or 30, whatever you got, the 460, the 81, the 1,000 kgs of coarse, 500, whatever it is, of fine, okay? And then that is your total design density. You've designed a cubic meter of concrete, all the aggregates, all the cement, all the fly ash, all the water, whether it's in the aggregates or you're adding it, makes up what a cubic meter of concrete would weigh. Okay? Now, excuse me, when you do a density test in the field, and let's say you were putting in exactly what your mix design said, the scales were so accurate, and your density was still low, then what? Why is that? Anybody have an idea what that would happen? I'm going to start recording here. Oh, we're back on, okay. Anybody have an idea? Air is high, right, Mitchell? Exactly. You got to understand that when you do a density test on the concrete physically, okay, and it doesn't equal your design density, air is one of the contributing factors, plus the accuracy of the scales. But I was just saying that if the accuracy of the scales were bang on and your weighing out was bang on, the difference would have to be to the air content, whether it's 7% or 6%. Now, when I gave you those fictitious values for lab 4, the mass of the concrete plus the measure, I was back calculating it. I was going to say this lab is going to have a, excuse me, is going to have a yield of under 0.1. This one's going to be over 0.1. This one's going to be 0.1. This one's going to be under. This one's going to be under. I just did it at random. Okay. And that's why I needed your total mass of ingredients. You know, your lab 3, I kept saying you got to balance it. You got to give me your total mass because I use that and I back calculate it. Okay. I know what your measures are because I've recorded those from the lab 1. So I know the mass of the measures you were using in lab 1, and I know what the, the bucket factor was. So I back calculate everything and give you that number. So I know ahead of time what your yield is going to be. Okay. Any questions so far?
Hey, John.
Yes, sir.
For the admixture, are we just leaving that at 0 mLs, or?
No, you should give it some milliliters. What is the range of admixture recommended?
That's a good question.
You didn't read Derivair 1400 spec sheet? How are you going to batch concrete if you don't know your products? You don't know your material. What do you think you got Grace as your ready mix supplier sales rep? He's selling you Aaron training agent or the Gusa. You're buying from him. You got to know how much to put in. You didn't look at the Derivair 1400 spec sheet, did you?
I must have skimmed that part. I must have glanced by it. But
Yeah,
I'll talk to my guy.
Yeah. You glanced by it, all right. You
I'll
probably
talk to my guy, my mix guy. I'll see what he thinks.
Is it 50 to 150?
I believe it's 50 to 180. I could be wrong. Somewhere you're right. No, 80 to 150, I think.
Okay.
Kelly's my mix guy, so thanks, Kelly.
I'm good. I'm only speaking from memory, and I mean I didn't open that this year, but I've opened it all the other years when we were doing a physical batch. But I think it's Pavel says minimum made 30. He thinks. I can't remember. I thought it was well, maybe it is 30 to 180. Somebody can correct me on that. Anyways, the spec sheet's loaded up. The technical data sheet on Derivair 1400 is in Learn. In Lab
What
4.
about that 541? Where is that coming from? Is that the City of Winnipeg 3441?
Okay. How did you do your concrete mix design? If you got 541, how'd you do it? Where did that 541 come from?
From you.
No, it did not. Were you around when we did that example of the concrete mix design?
Yeah.
And I went through the spreadsheet and we went step by step. And then I said, you guys now are going to do your own concrete mix design based on your aggregate parameters and based on your own group's data, density and so forth, and FM. How did you get that 541? What is 541?
Your cementitious factor, is it not?
Yeah, it's the total mass of cementitious made up of cement and fly ash.
Yeah.
And how did you get it?
We added the masses together.
Well, if you add it together, you had to come from somewhere. How did you get 541? And then how did you figure out your fly ash? What is total cementitious dependent on? I think you missed the boat on that one. You'll have to go back and it's based on strength indirectly, but what's the 184? The 184, 541 is fly ash and cement, right, Pablo? 184 is the water. So if you know the water amount, And what are we designing for? What's our mix design designed for? As far as water cement ratio? .34. So if you know that you're using 184 water, and you know your water cement ratio or water cementitious material ratio is 0.34, do you think that maybe 184 divided by 0.34
Yeah, that's what
give
it
you
was.
541?
Yeah.
Yeah, it's pretty, isn't math awesome, eh? And the water, 184, we determined that from the table where we're looking for a slump of 70 plus or minus 20. We know our maximum aggregate size. We know that those, or that table that gives you different masses of water based on different aggregate size, based on its shape, whether it's crushed or semi-rounded. We went into that table and we found out that we needed approximately 184 kgs of water if we're going to want to have a slump of 70 plus or minus 20. And then once we know water, and we went through the whole rigmarole of changing our water cement ratio, is because we've never had any performance data. We don't know if this mix design is going to work. The city only calls for 32 MPa. But then the standard deviation is your required compressive strength plus 8.5. And that gave us a design strength of 40.5 instead of 32. We go to the tables and the approximate water cement ratio for 40 MPa concrete, if you extrapolate, 0.34. Now, when you do your strengths, when you physically batch this concrete and you make your specimens and you do the compressive strength, you may find out that you're way over designed. Now, what you're going to find out and what actually happened in the previous labs is you're designed for 40.5 MPa, or say 40 MPa. And most of the students, their mix design, the strengths, came in at 42, 40, 43. You've met the city criteria of 32. No problem that way, by almost 10 to 12 MPa. But why didn't you get about 7 MPa cushion on 40? When you design concrete for 32 MPa, okay, the ready-mix producers, if their mix design isn't breaking at 37, 38 MPa, they're going to fail. 1 in 99 tests are going to fail. That's the cushion that you need when you're designing concrete. So when you, any of you guys that may have worked in the industry and you were testing concrete and the city spec calls for 32 MPa, the ready-mix producers' mix design has to be such that they should be breaking around 37, 38 MPa. If they're not, they're going to fail. One test in every 100 almost is going to fail. That's just the way it is, statistics. So you do not design for exactly 32 MPa because chances are you're going to fail it most of the time. You want to have that spread. Now that's 7 MPa, I just know that because it comes from industry. I've worked in it long enough to know. But if you read CSA, they tell you the statistical analysis that can occur. So those of you that have maybe even worked in the industry, and you know that you're always breaking at around 38, 39, 37, 38, 39, 36, whatever, for a 32 MPa mix. That's because it's done deliberately. You have to, or else you're going to fail. And nobody says anything, but as soon as a test fails, then everybody's up in arms. Everybody's up in arms. Anyhow, anything else before we get into our next units? Everybody good? Yeah? Okay.
Yeah, I'm good now.
I get winded, don't I? Long-winded. Anyways, I'm almost with Tyler Lay. If you've watched any of his videos they put up, Dr. Tyler Lay on his concrete. I listened to him speak in San Antonio. I was in San Antonio 4 years ago, 3 years ago, on a conference. And Dr. Lay was one of the speakers. This guy's just phenomenal when it comes to concrete, you know. I thought I was a geek when it came to concrete, but this guy's got me beat. Anyhow, and he's just so passionate. So he's got a lot of YouTube videos out there. And if you get a chance, get on his website, Tyler Lay. He's awesome. He's phenomenal. He's got a wealth of knowledge, concrete from a structural point of view, and actually from a materials point of view too. Okay. Okay. Let's go into the units that we're going to be looking at today. I'm going to share them up here right away. I'm going to move to the big screen here on my computer. That's why I sit sideways sometimes. I work on two screens here. So
These
my
are the
mic
units
is
that
on.
are going to be on the midterm, right?
What's that?
These are the units that are going to be
Yeah.
on the midterm, right?
The last 4 units, 7, 8, 9, and 10. So we're going to cover 7 and 8 this week, and then 9 and 10 next week. And again, these 4 units are all theory-based, essentially.
10 for good buddy.
What's that?
Said 10 for good buddy.
Oh, you like strictly theory? I look at the other way around, because theory, you got to remember stuff. You understand concepts. In math, you can almost do anything. You can almost solve for anything. Okay, let's go to share here. And this one up. And I want unit 8, unit 7. Okay. Can everybody see that? Okay. Okay, we've designed concrete, so to speak. We've looked at individual materials. We've looked at the water. We looked at the admixtures. Oh, by the way, what do you guys think of the quiz? Pretty good, eh? Easy. How many hundreds am I going to get?
Probably none.
None? Someone says the quiz was long? Oh, come on, guys. I've seen you guys have been finishing up in an hour and a half. Okay. Anyhow, I thought it was pretty good. I had no problems writing it. Anyhow, okay. We've looked at the individual materials. And sometimes I always think, is it best to look at concrete in general and then get into all the individual materials? But then sometimes when you're talking about concrete in general and you're tossing out fine aggregates, coarse aggregates, you might not really know admixtures, air and training agents, set retarders. You may not really have a good understanding as to what we're talking about. So that's why I take it in general, piece by piece. Now we're going to look at producing concrete. Okay. We did a trial batch, be it virtual. Okay. But now we're going to look at how they're actually batching it at the concrete plant. And unfortunately, this year and last year, we couldn't go to the plant to witness an actual batching. Because you mentioned earlier on that Michael, Rob, and I, we would go with the guys, the third year students, and we'd go to Lafarge's plant on Dawson Road and witness not only the precast plant, but we would go over and do the ready mix. So now we're going to look at producing, transporting, and handling that concrete. So this is basically related to the construction. And some of you guys may have been in the construction industry, and you may have already witnessed some of this or been part of it. Okay? So we're going to look at producing. We got to produce the concrete first before we can transport it and before we can actually place it. Okay? Okay. Now, ordering concrete. Okay, you're a contract coordinator. Some of you guys are going to be contract coordinators. And the contractor is going to order concrete for his job, and you may witness it. According to CSA, and don't worry about the -09, this hasn't changed. This is taken out of the CSA 823.1, and it's the same as the one that you have access to now, 19. 19 is just the latest edition. You can order concrete 2 ways, performance or prescription. The City of Winnipeg and MI, those of you that have maybe been involved, how do you think the specifications are written as far as concrete? Do you think our specifications are written from a performance base or from a prescriptive base? basically it's prescription. Those of you that have worked with MI, if you've ever read their specifications, they state exactly what they want. They even ask for the mix design. Remember we discussed that a few weeks back where I said, really, that's none of their business. It's a prescription. And you don't have to know all the columns, but know what a prescription base is. It's when the owner assumes responsibility for the concrete. So MI, if they're designing the mix, and their materials lab many times does, okay, then they're responsible. That's their concrete. The bridge department works a little different. The pavement group with MI would physically do the mix design. The contractor would come out, he'd set up a batch plant, MI would calibrate it. MI would give them the mix design. MI would test the aggregate. MI would test the aggregates as they're batching. So who's taking on responsibility? The owner. It's a prescription. And yet, when concrete fails at the job site, MI says to the contractor, okay, take it out, your problem. How can it be the contractor's problem? MI designed the mix. They calibrated the plant. They tested the aggregates. And now you're saying it's a contractor's fault? Something wrong with that picture. Yeah, pretty soon they won't. That's right. MI now is being dissolved, and their QC and a lot of the other work is going to be done by consultants, just like MTO in Ontario has done for the last 20 years, I would think. The performance is when the owner requires the concrete supplier to assume responsibility, okay, for performance of the mix and the placement, okay? When you guys or your relatives or your friends are pouring a driveway, many times you'll hire a contractor and say, I want a concrete driveway. Okay. Do you tell him how to design his mix? Do you tell him you want air between 5 to 8? More than likely you don't, because most homeowners wouldn't understand. They allow the contractor to do it. He's the expert. That is a performance. You tell him what you want, okay? But it's up to him to make sure that he delivers. And that's where the mix design statement comes in that we looked at, the city of Winnipeg. They want 32 MPa. They want 5 to 8%, okay? It's a class C2 exposure. That is what the mix has to meet. How the contractor / supplier designs and delivers, that's their responsibility. That's a performance. You want strength, you want durability, you want air, and so forth. So performance, and that's how we're leading to it now. MI and the city of Winnipeg have been prescription for so long, but now they're leaning toward performance, okay? Typically all over the world is more of a performance-based spec. We're always a little reluctant to change, okay? So those are the two alternatives. Performance, okay, that's one alternative, how you specify concrete, and prescription or method, but prescription is the term, okay? Don't worry about the other columns beside it. That gives you more detail as what is required to meet a prescription spec. For example, mixed proportions, including the quantities of any or all materials, okay? Admixture, aggregates, cement, materials, water by mass. So that's what a prescription is. The city is stating, this is how much cement I want. Or MI, this is how much aggregates I want. So in other words, they're doing the mix design, okay? That's a prescription. The performance is required structure criteria only, required durability criteria. Additional, you can give them additional. Maybe you want to share, you may have limits on shrinkage, for example, or durability. That you can give, but it's up to the ready mix producer and contractor to deliver that, okay? So those are the two methods of ordering ready mix concrete. Typical batch plant nowadays computerized. Everything is basically on a computer programmed. All the bins and all the gate openings are all controlled by the computer, water, the whole bit. I remember when I used to go do plant inspection years ago when I first graduated from Red River, everything was done with manual beam scales. The batcher would physically go and grab a lever and open the the bin and all the aggregates would drop on the scale, and then he'd close the bin. Okay, as the scale is starting to tip. It's a beam scale. I don't even think they were digital back then, or dial even. Okay, a lot of them had those beams. Okay, they are. But now everything's on the computer. He's got a mix design, he's got a code, computer feeds it, controls the gate openings, controls the pump for water, controls the admixtures, and so forth. So this would be a typical operation that you would see. And outside here, he physically has a window usually, and he can physically see, did he get the certain milliliters of air training agent? Sometimes it's good to have a backup system so he can physically see, yes, it's going in. But the amount of metering the admixtures, whether it's air training agent, super plasticizer, water reducer, whatever the case may be. So this is just a typical control room. Okay, what is the definition of batching concrete? Okay. Is that the 80s or 90s? Tim, you're asking me, sorry, about when I was batching? That was mid-70s.
That was a picture of you?
That was a picture of me. No, that's not a picture of me. But I remember sometimes the batchers. There was one batcher with Winnipeg Supply. He used to hit the bottle at nights pretty hard. He'd come in one morning and he could barely stand, and he'd open the gate to drop the aggregates, still hung over. And then the aggregates are spilling out. And it takes a lot of force to close those gates, because you got to remember the hoppers up top open up and you're dropping aggregates for 5 cubic meters of concrete. So he's going to try and shut the gate. Well, he could barely stand, so he couldn't close it. So he overloaded the whole scale, and they finally brought another batcher in and they sent them home to keep it off. But that was all manual control. So that goes way back. Okay, it's been quite a bit automated since. But yeah, that's back in the 70s when they had the old beam scales. Yeah. That just ages myself, guys. Okay, the definition of batching concrete. It's a process of actually measuring concrete mixture ingredients by either mass or volume. Typically, majority of it is mass. If you might be in an isolated area, remote area, you might do it by volume. I've done it by volume. When I was in Cross Lake many, many years ago, we were building an RCMP detachment. And I physically just calibrated the loader bucket. Figured out how much aggregate I needed for a cubic foot of, back then it was cubic foot, it wasn't even metric yet, a cubic foot of aggregate. You know, I had the carpenters build me a cubic box, 1 foot by 1 foot by 1 foot, and I filled it, took it to the airport, and I weighed it because I knew they had scales there for luggage. So I determined how much a cubic foot of aggregate would weigh for my mix design. And I knew how many of those boxes I needed for, say, we were batching 0.5 cubic meter at a time, depending on the size of the job. So I dumped in 0.5 cubic meter of aggregate into the loader bucket, leveled it off, marked the inside with a felt marker to make sure that he always had the same amount. It would level it, dump it into the mixer. So there's ways of doing it. Obviously by mass, when you can weigh it on a scale, it's a lot easier and a lot quicker and a lot more accurate. But it can be done by volume. Okay? And again, most specs in the States would be ASTM C94 here. We're controlled by CSA A23.1. And if you go to table 24, you'll see that there's tolerances for batching. We're not going to look into that, but there is. The scales have to have a certain tolerance or or accuracy, as does the cement scale, as does the aggregate scale, as does the water scale, admixtures, and so forth. But the definition, batching, it's a process of accurately measuring the ingredients for a concrete mixture, mass or volume. Okay, and there's the batching tolerances. I'm not going to go into it, but you can see that there's a plus or minus 2, and it depends on the capacity of the scale and the degree of the scale. And there's what's called separate batching and cumulatively batching. Anybody know the difference between separate batching and cumulatively batching?
One you do separately and the other one you do cumulatively?
Good guess. Yeah, exactly. In other words, your mix design, let some of you had 495 kgs of sand and say 1,000 kgs of quartz. On some scales, you could weigh up to 495 and dump it into the hopper. Some plants you would put on the 495, then you'd add the coarse aggregate on top of it until you were reading 1495. That tells you you put on 1,000 kgs of stone or coarse aggregate because it's cumulatively. So 495 bisulfite is the sand. You add 1,000 on it, okay, and then so that's cumulatively. So it depends on how you're batching. The degree of accuracy is going to change, okay, because you're using larger masses. Okay, batching concrete. How accurate is that equipment? And this middle one here about the certificate, I like this because I always throw this on an exam and I always catch people on it, true and false or whatever. A certificate of accuracy. In other words, each plant has to display a certificate of accuracy that is not over 180 days old, shall be provided for the scales or measuring devices by a qualified technician employed by a certified scale manufacturer or scale company. Okay, so in other words, those plants have to be calibrated, and they might use Toledo, they may use superior scales. Okay, and it's got to be done frequently. Can't be any older than 180. So in other words, if an engineer comes into the plant, you should be able to see that certificate that that scales of that plant and the measuring devices have been certified by, say, somebody from Toledo Scale, qualified. And usually they'll check it in accordance with the national standards, Canadian standards, or they may weights and measures, that type of thing, okay? Now, that's 180 days. So let's say you got your plant calibrated, and then all of a sudden you got a problem. You got to take it apart. Something broke, you got to weld it. You dismantle the scales, you dismantle the bins and everything else. You brought in some extra steel, you did some welding, you got it up and running again. You got to recalibrate it because you've altered the weighing mechanism. You've altered it by taking it apart when you're repairing it. So now you got to bring in the plant again. Sorry, you got to bring somebody in from the scale manufacturers or from the calibration company, I should say, and recalibrate it. Even though you may have just calibrated 2-3 weeks before that, 2-3 days before it. Tough apples. Life sucks. Okay? So recalibration has to be performed after plant relocation or major alterations. Plant relocation is those portable batch plants. Let's say you're paving Highway 75. Nelson River, for example, if he was paving Highway 75, he would move his plant from his yards in Winnipeg. He'd set it up at the job site. They'd have to bring out Toledo or Superior Scales or ProTech, whoever they use, and calibrate it. And then they get a calibration certificate saying that the scales are accurate to within the tolerance required by the Manitoba Ready Mix Concrete Association. They're usually the ones that dictate it, okay? So you got to recalibrate it. When you relocate the plant or you've done major alterations or repairs to it, okay? Keep that in mind. Now, there's all kinds of plants, okay? There's central mix, there's dry batch, transit mix, there's mobile mix, okay? This picture here shows a central plant, okay? It's a stationary mixer. You can see a central drum discharging concrete into the dump truck. A dump truck for concrete? Is that legit? Is that acceptable, guys? Girls?
No.
Why not? You're showing it in the picture. Why not? Why isn't it acceptable?
Does it not just start setting in the truck without being mixed?
It can. If it's not being mixed, then a revolving drum mixer can start setting up too, eh?
Yeah.
A revolving drum mixer does it. No, that's acceptable. We use that at Centerport. Okay? We had Miller Paving out there. You go to any major highway job in the States where there's large volumes of concrete, or even Toronto and Vancouver and bigger cities, if you got to make production, you're going to use 18-meter semi-trailers for dumping concrete. But yeah, you're right. There's some stipulation. Because you're not agitating it, you got to make sure that when you get that load of concrete, you do deliver it, and you deliver it as quickly as possible. and you do it over relatively smooth roads. Okay, so you don't bounce all over the place and they'll start to segregate. Typically, you're going to use this for highway work or city work. You're going to be using a slip form paver. So you're going to be using stiffer concretes to begin with. Okay, when you're using a slip form paver, which is an extruder, okay, the concrete goes through the machine and you get 200 milliliter thick pavement out the back, no forms on the side. You don't want it to stand up. Okay, so no, that's acceptable. That's acceptable. I know MI, when they were doing a half of Centerport, and I was with a consultant, we were doing the other half. We used tandem dumps, semi-trailer dumps. They went strictly revolving drum mixers. They didn't like the idea, but we got permission from them. We actually went down to Toronto to witness a job like this going on because MI was a little concerned. They've never done it. You know, they don't keep up with technology. This is how it's done in most places. Huge jobs when you want to pave 2 kilometers of highway a day, where you may be producing over 1,200 cubic meters of concrete. You got to lay it down, and you got to lay it down fast. Okay, you only have 24 hours in a day. Okay, stationary mixers, they can be on site, and ours was like this. We had set it up on site. Miller Paving erected it at a central drum. Okay, central mix. Lafarge on Dawson Road, that's a central mix plant. It's stationary. It's always been there. They deliver concrete from there all over the city of Winnipeg. Okay, I'm not going to get into size, volumes. You know, they can batch, depending on the drum and the scales, sometimes they can batch 9 cubic meters in one shot. So if you use a large semi-trailer revolving drum mixer, some of them carry up to 12 cubic meters. Okay, but the size of the load is going to be based on the size of the central mixer. What's the capacity of that? So you got stationary mixers, central mix plants. Okay, there's a plant set up there, ready mixed. But in this one here, this is not a drum plant. You can see the scale, the hoppers up there for the aggregates, the scales, it drops in, the truck becomes the mixing plant. Okay, this is a truck mix concrete, sometimes referred to as transit mix, because it's the transit is being mixed as it's going up to the job site. So every truck becomes a mixer. And using a dry batch, these are sometimes referred to as dry batch or truck mix or transit mix, they're a problem because each truck is different when it comes to batching. Some may be old and worn and doesn't mix the concrete very well. So you can have very large inconsistencies between loads because you're relying on the drum on the trucks to meet, to actually batch the concrete. Okay. So you get the when we refer to shrink mix, they're basically saying that you would mix it in the truck at the plant, and then as it's heading out to the job site. Okay. Truck mix is exactly what it says. It's in the truck. Same thing. Central mix, again, here you can see just a different sketch here where there's the central drum discharging the concrete. So in other words, before this concrete goes into the back of that revolving drum mixer, it's got to be mixed properly at the plant in this large drum. Okay, and the batcher in the control room will determine, based on speed and revolutions of the drum turning and torque, he'll be able to determine whether that concrete is well mixed in the drum here before he drops it in. When it travels to the job site, it's not mixing, it's agitating. It's just keeping the concrete moving. Okay, when this guy gets his load of concrete, it should be already well mixed at the central plant. All the truck is doing is he's a delivery media. Okay, and he's agitating it to keep it moving, keep it flowing between point A and point B. Okay, it's delivered to site in a truck agitator. Truck mixers operating at agitating speed. That's why you can also use a semi-dump trailer. You're not, okay, it's short distance, it's not going to set up. Okay, you're not mixing. It's already pre-mixed at the central plant. So really all you're doing is you're hauling it from A to B. And when you're using dump trucks, it's got to be a relatively short distance. It's got to be relatively smooth so the concrete doesn't have a tendency to segregate. In other words, the separation of aggregates from your paste. segregation. Okay, any questions? Here's just sort of a schematic of a central mix plant. Don't worry about it. I'm not going to push you on it, but you can see the various components where the aggregates will come in. It won't come in here on a barge for us, but it'll come in on rail cars, those tracks that run through Lafarge. If you notice, there's a set of railway tracks that goes to the precast plant. Well, they get their aggregates coming in by rail car. Then you'll have bins for various aggregate sizes. You'll feed it up to the plant. Okay, you have separate bins for your separate materials. You may have two coarse. You may have a sand bin. You open the gates. You weigh out the coarse. Stop it. Once the computer cuts it off, you've loaded your coarse aggregate. Goes into the mixer. Water is added. It's mixed. Dropped into the delivery truck. This plant here, we'll look at it here. You remember in water, tendency nowadays, maybe not so much here in Winnipeg, but is to recycle your wash water when you wash out your drums. Okay, after every load, you want to wash out your drum because you're going to get another load of concrete. Your wash water now is going to have concrete in it. You know, not a lot, but it'll have some because it's washing the inside of your drum. So now they're recycling their water. Okay, they'll have a settling. A lot of the heavier aggregates will settle out, and they'll have water going up with cement and paste. And they'll have to know actually what's going here. And here you can see that they're pulling out the fines that get washed out with the wash water, and they may reuse that back in or whatever, or use it for grade or base course or whatever. Okay, so you can see they're recycling their water. Transit mix, okay, referred to as dry batch, whatever. Transit mix concrete. When you get concrete delivered to the job site, whether it's from Lafarge's central plant or when it's produced at a truck mix or dry batch or transit mix, whatever you want to refer to it, whether the truck mixes it or whether the central plant mixes it. Remember, I had mentioned earlier on that hydration starts as soon as water and cement come to play. Whether that water is coming from wet aggregates or whether you physically are starting to add water from the pump at the plant, that's when hydration starts. From that point on, according to CSA, you have 120 minutes to discharge that concrete into the forms, which would mean batching, travel time, discharge time. Now, I know some of you may have worked for the city and MI, they're using 90 minutes. I mean, that's their spec. I don't agree with it. 90 minutes is ridiculous. Okay? It's true. The quicker you place concrete from the time of batch, the better off. No two ways about that. But there's nothing wrong with 120 minutes. But MI and City of Winnipeg are a little reluctant to change. They haven't kept up. So you've got 2 hours. And that's why some of you may have been on a job site where you've looked at a ready-mix ticket. If you're inspecting placement of concrete for the City of Winnipeg road, you'll look at a delivery ticket and you'll see a timestamp. Every delivery ticket has a timestamp. And that time should tell you as an inspector, should tell the contractor, superintendent, whatever, that the water and cement came in to play at 12:30 p.m. They started batching that load. From 12:30 to 2:30, it's got to be discharged in that time frame, maximum. Which isn't always right, because that time stamp 12:30 is not accurate. Because they never punch the ticket until the guy leaves the yard. So they're batching concrete. The driver gets his ticket. He knows he's going to Manitoba Hydro building, whatever the case may be. He stops and he shoots the breeze with his fellow driver, and he goes up to the plant. He goes up and he grabs a coffee from the coffee room. He shoots the breeze with the batcher. So now his truck's been loaded for about 15, 20 minutes. It's revolving in the yard. He's having a coffee. Then he says, well, I guess I better get up to the job site. So he goes and he punches the ticket. 20 minutes later from when the water and cement came in. The inspector gets all alarmed when it's already on the job site for 2 hours. Well, actually, it's been there for 2 hours and a half almost. But he doesn't know any better because he looks at the time and it's stamped 12:30. But he got batched at 12:10, whatever. Okay? But that's why it's important. It's when the water and cement first come. Hydration is going to start. Okay. Well, these are little secrets that I always had to do because I used to spend many hours up in the batch plant when we used to do City of Winnipeg plant inspection. Years ago in the 70s, every time the City of Winnipeg was placing concrete, major roadway, not back lanes or driveways, or approaches, I should say, but major residential streets. When I was junior, I would be at the plant, or then when I became a manager, I'd set my people up. They would be at the plant and they would witness and they would sign when the actual guy, when the water would come together, not when the driver punched it. It was the inspectors at the plant signature that the field inspector would notice, and he would go by that time, not by the delivery time that the driver would stamp because they know what's going on. Anyhow, 2 hours from time of first contact, cement and water. Any questions? Has anybody ever seen this mobile mixer here that I'm looking at, this white truck here? Okay, and then you got a concrete boom, you got a concrete pump. Anybody ever work with these mobile batching mixers? No? Anybody ever see a Stephen Chuck concrete running around the city of Winnipeg? They'd have these trucks. I think ABM Materials also has it. This is actually a concrete batch plant. Okay? These are a little bit difficult to calibrate. You gotta know what you're doing because you can see here in the back of the truck, he's got dry ingredients. He's got dry cement, he's got dry sand, he's got dry aggregates. And he doesn't have a scale. It's mixed on an auger. The speed of the auger and the material coming out of the truck has to be calibrated such that when the dry ingredients get mixed on the auger with the water, and by the time it comes off the end of this small conveyor, it's got to be mixed. So you're not weighing out aggregate by mass. It's strictly based on time and the speed of the auger. These are hard to calibrate. The beauty of these is, okay, you've estimated you need 10.5 cubic meters of concrete. How many times you've been on a job site where you're short? Now you got to wait for the last load. Here he just keeps mixing. Once the box is filled, the forms, he's done. No waste, no under, no excess. Because he's continuously batching until he fills the forms. So it's good in a way, but the fact is the consistency of it sometimes is in question. If these things aren't calibrated properly, your mix can create havocs with you. Mobile batchers measure materials by volume and continuously mixes concrete. As the dry ingredients, water, and admixtures are fed into a mixing trough at the rear of the vehicle, and it's an auger that mixes it. So in other words, it's being mixed on an auger, almost like a grain auger. Except instead of grain, you're going to have your dry ingredients. The advantage, combined materials, batching, and mixing all in one. So that's an advantage, but a disadvantage, and I've highlighted these because these are sometimes questions I'm going to ask. What's an advantage of having a mobile mixer? What's the disadvantage of having transit mix versus central mix, okay? You have to really watch the maintenance program because if these augers and speeds and that get built up and they don't get properly maintained and they're not turning consistently, you're going to have problems, okay? And it's typically like any other mix design, the material should be identical to what your mix design is based. It's a little different than batching concrete at Lafarge's central plant. You do a mix design on the aggregates, it should be the same aggregates that Lafarge is going to be using at the plant. So these are mobile batcher mixers, okay? And a lot of times the central guys like Lafarge that don't own them do not like them, okay? Because they're interfering with their system. The ready-mix producer has to go through a fairly extensive calibration. Okay, the scales, the plant, the trucks has to be approved every 5 years. The ready-mix producers have to have their facilities inspected by a qualified engineer. And not only the scales, the working operations at the plant, the revolving drum mixers. Are they turning at the right revolutions? Do they have a good system of fins inside the drums? Or are they all worn down? You got to remember, if you look into a revolving drum mixer, there's fins or baffles, and that gives you the shearing of the concrete. Well, sometimes those old mixers could be 15, 20, 25 years old. Those fins inside eventually wear down, so they don't give you a good shearing action. That's why a transit mix, you can have inconsistent loads because every truck is different. Okay, mobile batchers. There's your non-agitating trucks. Okay, they're used for concrete on short hauls over smooth roadways. We use that at Centerport because our plant was right in the middle of the job site. So we could go from the plant to where we were placing the concrete within less than 5 minutes. Okay, they had a dedicated road, and most of these will have a dedicated pathway, so you know there's not going to be any vehicles. You leave Dawson Road at 4 o'clock in the afternoon, okay, to get down to St. James, rush hour. That 2 hours is going to be pretty tough to get from Dawson Road to St. James and discharge the concrete. Okay, so these have a lot of advantages from that respect. They're only geared for the project, site specific. Lower cost than truck agitators. That's why we use them. We can move a heck of a lot more concrete quicker and cheaper than we can with revolving drums. And when you have large volume pours, great way to moving 18 cubic meters of concrete versus 7 loads, 7 meters, 7 meters, 7 meters. Most ready-mix trucks, other than those big crane carriers that you see in Lafarge or even City Mix, they only have 2 or 3 semi-trailer revolving drum mixers. Most of them are about 7.5. Some of them are even 5.5 maximum cubic meter mixers versus a semi-trailer that can haul 18 cubic meters over a short distance. Okay, 3 times as fast. But again, you got to be careful. Slump, you got to have basically not a wet slump because you'd lose it at the tailgate. Those things don't seal tight. Possible segregation, if that road was really rough and bouncing all over the place and your concrete was a little on the loose side, your aggregates would start separating or segregating from your paste. Plus, if you're working in a congested area with overhead power, check your overhead. Can you boom up? Can you lift this truck box up to dump in front of the paver? Or is he contending with hydro lines, whatever the case may be, towers? Okay, so there's some pluses. There's also some negatives, but great for large volume jobs. Ideal. And then I've never seen any of these around. I think these are actually an agitator truck. They don't revolve, but the back just kind of shakes. Okay, you can see my hands. It kind of shakes. So they're called agitator trucks. Okay, again, short distances, 2 hours maximum. 2 hours also for the hydration process. And they typically operate from a central plant. Okay, you're not going to have a dry batch because you can't dry batch. Disadvantage, you got to be really cognizant of your time limits. Okay, and again, if it arrives on the job site, you got to be ready to dump it. You don't have much time. Revolving drum mixer, okay, if you're delayed for 15 minutes, then you know it's being agitated in the drum and you're still within the 2 hours, you're okay. But these, if they stand there, this one's agitating, it's not bad, but the other dump trucks, if they were standing and waiting for an additional half hour, that'd be a problem. So there are advantages, like I said, and disadvantages. Revolving drum mixer, the advantage is you can keep agitating it, but when it comes to large volume pours, it takes you for so long. Economics, okay? So these are called agitator trucks. Okay? Any questions so far? Holy mackerel, 2 o'clock already. Remixing concrete. Can you add water to concrete on the job site? Oh, Clive, you said the Nelson River has an agitator truck? Is that what you're referring to? You can speak up if you want, Clive. Yes. Oh, is that right? Excellent. See, I've been out 8 years out of the field now and I'm losing touch. Okay, thanks. Can you add water to concrete on the job site? Legally. I know every contractor says you can, but can you? Anybody? You can blurt out your answer if you want by audio. Yes, you can. But again, you got to know what you're doing. Okay? You can add water, provided you don't exceed the water cement ratio. You can always check at the plant because they know exactly how much water they've used. If they're batching under the amount of water, then you know they haven't exceeded it. If the slump that you measure is less than what's needed, and that's at the start of discharge, okay? Not halfway through the load. You're starting to dump, you want to check the slump, you check the slump and it's way under, okay. Plus, you do that within the first 60 minutes of the time the cement and water come together, okay? So in other words, within 60 minutes of batch, you can add water to the job site. You can add water, okay? There's also a certain amount that you can only add, and that's in CSA, it'll tell you that, okay? Now, then once you add the water, you have to mix it, not agitate it. 30 revolutions at mixing speed. A lot of times you'll see contractors add water. They add water, they give it a couple of turns, dump it out, stiffens up again. Hey, I want more water. So they add more water, you mix it 3-4 times, dumps it out. First couple of wheelbarrows come out, slump is good, then it stiffens. You're not getting that water that you added the first time to the front and the back of the load. That's why you got to have a minimum of 30 revs. And you can physically count that. And not at agitating speed, at mixing speed. And there's a plate on the truck that tells you what the revolutions are, RPMs, at mixing speed and at agitating speed. Now, if you got super plasticized concrete, that's concrete that has super plasticizer in it to give you a high workable slump, then you can't add water. You got to retemper. When you add water to concrete to bring up the slump, it's called retempering. So you got to retemper with Super P. So in other words, if it's a Super P mix, don't add water at the job site, add the Super P. And usually when you're retempering, when you're adding water, especially Super P, you may have to fix up the air because the air may be out of whack. So then you can adjust the air also. So remixing, adding water on the job site's allowed. If you see an old spec that says you can't, that spec's old, shouldn't be around. Okay? Transporting, we're going to quickly go through this. I was going to get into the next unit yet before the lab, but that'll be pretty straightforward. We'll have a break here right away, we'll do the lab. But transporting and hauling, okay? So you can see here the various trucks. Here's a front discharge truck. I haven't seen any in Winnipeg here. There might be. But they have them in Toronto. But that's great because the driver sits in there. He can control it. He sees exactly where he's going. He doesn't have to back up to the forms. Somebody doesn't have to direct them and hold the chute. He can control that. He can move right up to the forms, raise his chute, reposition it. He's in the cab. He sees it at all times. These are great. These would be great. I haven't seen any in Winnipeg. I'm not sure if we have any. Maybe, maybe not. But and they look funny, right, Tim? Laugh out loud. But they're ideal. They're ideal. Choose appropriate handling method. That's going to be based on what? Well, we've got to look at what system are you going to use, or what method of transporting, what method of handling concrete are you going to use. It's going to be basically project dependent. Okay? Choose the appropriate handling method. Consistency affects the selection of the conveying method. Okay, we know that a slip form paving job, a highway, or a city, you're going straight. It's consistent. It's the same thing. Okay? So yes, you can use 18 cubic meter dump trucks, or you can use 7 cubic meter revolving drums, 2 of them back up, 1 on each side of the slip form. He dumps it and away they go. How easy is it to the job site? Okay. How high are the forms? Is he going to be discharging concrete down into the forms, or the forms higher than the back of his truck? You can't push concrete out of the ready mix truck up the chute. You can push them down. Well, maybe he's going to need a crane bucket. Maybe he's going to need a pump. Okay, height of placement, dimensions of the form openings. Okay, is the end of his chute going to be able to fill that narrow width of a wall? Could be a very narrow wall, could be wide. Okay, things you got to take into consideration. Deposited concrete as close as possible to its final location. You never want to move concrete horizontally. You want to drop it in place as close as you can. If you ever see anybody moving concrete horizontally with a vibrator, you take that vibrator and throw it away. You never move concrete horizontally with a vibrator. We're going to segregate it. Okay, you drop it in place, you're going to vibrate down to consolidate it, get rid of the air pockets, not move it sideways. Okay. I put height of free fall. If too great, use a tube or elephant trunk. I don't buy this. You still see it written in specs. That's a crock. MI force the contractor, anything over 5 feet drop, they want them to either pump it or use an elephant trunk. Okay, elephant trunk is just a, we call it an elephant trunk because it looks like the trunk of an elephant, but it hooks on the bottom of a chute of the bucket, and you lower it down to where the concrete is going to be placed. In other words, if you're doing a caisson that's 40, 50 feet deep, okay, they're saying you can't drop it more than 1.5 meters. Well, you know, guys, I was on the hydro building. I was on the construction of the MTS arena. I've been on construction on the Holiday Towers 1 and 2, well, mostly the convention center. But more recently was the MTS Bell Arena. And we were dropping concrete into a caisson that was 60 feet deep. Okay? We had cage, a rebar in it. We would back up 2 ready mix trucks, put both chutes down, and we'd let her fly. That concrete was dropping 60 feet. No segregation. The old way of thinking is that your concrete's going to segregate when it hits impact. There may be some aggregates pinging off if you're hitting the cage of rebar inside the pile. But if you're dropping it straight down, and Subterranean did a study, and there's been studies all over, and even ACI design manual has no restriction. You can drop that concrete 60 feet and it won't segregate. There's been studies taken where they've cored the center of the whole caisson 60, 70, 80 feet in depth. They pulled that concrete core out. There's no sign of segregations yet. When I was at Centerport, and then I left Centerport to come to the college, but I kept in touch. MI forced Subterranean to pour the concrete for those big lamp standards that you see as you're going up on the overpass, the lighting standards and the sign standards for your directions. They were only maybe 8 meters deep, caissons, because bedrock was close. They had to pump every one from the bottom up. MI would not allow them to drop that concrete more than 5 feet. Hey guys, there's something wrong. We've shown, we've proved, there's articles written on it, and I've even got one here. I should upload it to you guys, put it in for reference material. There's numerous papers are written. And even the ACI code for design has no stipulation that tells you that you can't drop concrete more than 5 feet or 1.5 meters. Yes, you don't want to segregate it. Like you try and drop the concrete through the cage, because typically in a caisson, you've got vertical bars running around the perimeter, and you've got the round stirrups to hold the cage in. So you can drop that concrete in the middle, so the aggregates don't ping on. Your concrete is going down in one homogeneous mass. Still specified in numerous specifications. MI. I don't agree with that. I'm going to take this out, I think, in futures. And when you're depositing concrete, you want to do it in 200 to 500 millimeter thick lifts. Like a basement wall, you want to go around it, eh? Okay. So important points here. Okay. Size up the job, size up what you're placing, the consistency of placement, any overhead barricades that may stop you if you can't use a dump truck or whatever. Know what you're doing. How's your forms? Are they accessible? Are you going to need a concrete pump? Okay, and you can see various elements here. This is wheelbarrow. That's how most of us started and still used to this day. Sometimes that's the only way you're going to get concrete in, by wheelbarrow and manpower. Or you may have power buggies, okay, wheelbarrows and buggies. Here you have a concrete pump, okay. A lot of homes now, even residential, are going to pumps, because with the narrower lots, at one time a ready mix truck could get into the back or between a house and a new house being constructed, and he could actually pour the basement walls going around. Now they can't. So you'll see on most residential constructions, they're using a pump. Okay, they'll park the truck on the front street, ready mix producer will come up and he'll boom over and he'll pump it into place. I'm going to leave the information as far as advantages and disadvantages for you. But here you can see that he can reach quite a bit. We had such a long reach at Centerport one time that a pump wouldn't reach it. So what we did is we got the contractor to bring out 2 pumps. Okay, so we dumped the concrete out of the ready mix truck into 1 pump. Then that pump, he extended his boom as far as he could go. And then here, with this chute, he pumped it into the next pump. Okay, just like a ready mix truck would dump into the hopper of the pump, we were dumping into the other pump from this pump, and then he boom over to the other. So we basically had 2 pumps in tandem. So we were able to reach further out because we were doing a box culvert in winter, I think it was, and we couldn't get access. So it was costly, but we got the job done. Okay, so we pumped truck into 1 pump, and then that pump pumped into the next pump, and then that next pump dumped into the forms. So there's a lot of ways of skinning a cat, eh? Okay, here some trucks will have an additional conveyor. Okay, so the concrete comes off his chute, he drops it onto conveyor, and then this conveyor takes it over to the job site. Sorry, to the forms. So again, I think some of them have that. I know some of the, I think Lafarge has one of these, because that's actually how we get their aggregates into car seat, because they bring the concrete in a ready mix truck, sorry, the aggregates only, and they dump it for us using a conveyor because they can't back into the building. Yeah, that would save time for pouring. 2 buckets, you've probably seen these on high rise. Okay, you've got a tower crane on the middle, and they're doing floor construction. Okay, floor by floor. So they're using a bucket. The bucket sits on the ground. The delivery truck, ready mix, dumps it in. Crane lifts it, swings it over to the 10th or the 12th floor, wherever they are. So they're using buckets. Very, very common. You can see a congestion of steel here. And again, you should be dumping this really close by here so that you don't have to move it. So he's going to fill this up, and he's working off a platform here, okay? Again, you can use cranes, cableways, helicopters, okay? You're in some areas, remote areas, or you can't access even a crane, you'll use a helicopter. Very costly, but you'll do it. There's a tower crane in action, okay? Cranes and buckets. Another pump. Yeah, he's parked over here. He's set up. He's got his outriggers set up. Delivery truck dumps it in. He pumps it and down. The best thing to do is try and keep your boom as horizontal as possible without too many bends in it, because it affects your air. And that's just another matter all to itself. There's so many articles written and people wanting they say you lose air. Your air content may be great at the end of the truck. When you pump it, you lose air. So AMI gets really upset. They say we want the air tested at the end of the pump. Where does the air go? You don't lose it. And Tyler Lay, and I'll send you guys that video. He's got a great video that I've sent to a lot of the other testing agencies to look at it. And he made a research study on it. And he just says, you don't lose air. It's there. It's going to be in the forms after. But yet, when you do your air concrete test at the end of the pump, and you need 5 to 7, and you're only showing, for some reason, you're showing 4.5, you've got it. It's in there. It'll come back. Okay? Temperature, bubbles, dissolving.
Is that the Aaron trained videos?
Not the one that I put up. There's another one that specifically talks about loss of air by pumping.
Oh, okay.
And I'll put that one up. Okay. So again, pumps. Conveying concrete from central discharge point to formwork. And quite common used here, obviously, okay? And here you can see that the last part of the pump usually has a flexible elephant trunk if you want, and he's depositing the concrete. I don't know, to me, most of these guys still hold it about that height. And when you're working around it, you just get splattered. I don't know why these guys just don't lower it another half a meter or so, just so the concrete wouldn't splash all over you. And here's the guy on the vibrator vibrating the concrete. The next slide, the next presentation, sorry guys, I wanted to get through it, but we won't have time, is it tells you there's a right way and a wrong way to vibrate. Here in Winnipeg or here in Canada, the guy on the vibrator is usually the guy that has the biggest hangover in the morning because he's useless for anything else. In Europe, you don't pick up a vibrator unless you're certified. You have to know how to vibrate. There's a right way and a wrong way. And you can create problems if you're vibrating wrong. Okay? Now this one here is probably electric. A lot of them now have battery packs. So he doesn't have to drag this hose, sorry, not hose, electrical cable. So a lot of vibrators now will have a battery pack and he'll run off the battery pack and he's pretty mobile. Okay? Slip form auger, screw feed they're called, slip form. You can see the concrete is deposited on grade. Slip form paver, as he's moving along, he's going to move that concrete back and forth with these augers. He's going to distribute it nice and evenly so it feeds into the extruder at the proper height, and then he'll have the concrete. Okay? These should be used. They should be used for spreading before vibration is applied. Well, this machine is self-contained. The vibrators are in behind. As the concrete gets pushed in, with the augers after it's leveled, vibrators are on the back of the screed. And that's what gives you your nice homogeneous mass out the back. Screw spreaders, refer to them here as slip form pavers. And here you can see in an area where you might use a helicopter and a bucket, or you can use a crane here. Sometimes these cranes can be set up at an upper floor, so you'll pump up to this one, and then from here you'll pump out. The Burj Khalifa in Dubai, most of that concrete I think was pumped. You can pump concrete phenomenal distances if you have a pump mix. The mix design that we did in our lab, you would never use that as a pump mix. Okay? So you can have a 30 MPa mix for slabs, you can have a 30 MPa mix for columns, you can have a 30 MPa mix for grade beams, and you can have a 30 MPa mix that you want to pump. They're all different proportions. You're not only going to have one mix for everything. The mix that you guys are coming up with, 65, 63, 69% coarse aggregate, it would be quite difficult to finish for a nice finished floor slab. It's not enough butter. It's not fatty enough for paste, for finishing. What you need for a floor slab. Column, grade beams, who cares? What do you finish? 200 milliliter wide top of a grade beam and formed on all three sides other than the top? You can have a harsh mix. You can have probably a 73 mix, which is great. Better strength. Anyhow, the next unit I wanted to get into, Unit 8. If we have time somewhere along the line, maybe we can. If not, I would suggest you guys read it. I want to take a 15-minute break here, a 10-minute break, let's say. I'll just pause the recording, and then we'll start on the labs. Any questions? Sorry, it took a lot longer. Yeah, link. Okay, yeah, there is a link for Tyler Lay, and he's got a playlist. Because once you get into his mix, Tyler Lay's videos, he's got one after the other, one after the other. So he talks about anything and everything. And I've actually got videos put out by the Ontario Ready Mix Concrete Association that tells you how to do the proper tests for slump, air. And these are the tests. And they put these videos together specifically for the ACI Concrete Testing Certification course, because our ACI, we base it on CSA spec. So all the videos that you see out there for ACI Concrete Testing Certification were American, based on ASTM. And ASTM are different. But finally, Ontario Ready Mix put together 6 videos for the 6 main tests that you would be certified under here in Winnipeg. If some of you guys are signing up for the course in May, it will be based on. So I finally found them on YouTube, and Ontario just put them out, I guess, last year. And I gave them over to Bree Williams, because she'll be the instructor from Red River that'll be doing the theory part. So I sent her those videos, and she was happier than a pig, and you know what? Okay, she was really happy about them, because a lot of the videos out there are wrong. And if any of you guys have looked at some of those videos that are done, slump test, the air test, forget it. They're just totally garbage. Anyhow, let's take a break. It's 2:24. Maybe we can confine the lab to only a half hour, and then we'll be done by 3. This took us a lot longer. So it's 2:24. So is 2:35 okay if we come back? Say 10 minutes for a coffee? Everybody okay with that? Yeah? Okay. I'll stop the recording and we'll come back here. We'll do the lab for compressive strength and flexural strength. And we'll take it from there. So let's go for a 10-minute break. 2:35 is 2:25 now, okay? I'm just going to pause it. Okay, everybody back already? Everybody still having coffee? Okay, let's, we'll try and wrap this up in a half an hour because I'm sure you guys are pretty tired. Compressive strength of concrete and flexural strength of concrete. I'm going to put the recording back on. Okay. You're going to have to access the CSA standard, flexural strength of concrete, 823.2-9C, and flexural strength is 823.2-8C. Those are pretty detailed specifications or procedures for testing concrete. I'm going to try the video today that I've found for these two tests, and I'm going to need some input from you if the video is working on your end. At one time, I tried to do a video through WebEx, a YouTube video, and it wouldn't go through. It actually was more of a frame by frame, not so much a video. If that's the case, then the video you'll have to watch on your own. And again, when you're watching a video, whether it's for a lab or whether it's for a lecture, keep in mind that a lot of these videos, especially the lab ones, I'm interested in you learning the mechanics of a test. Sometimes the numbers they use, the value they use, the data they use can be from ASTM. Here we're referring to CSA, so have the CSA procedures with you. We're going to look at a video here where they're going to be testing concrete, and they're going to use steel caps with neoprene inserts. We don't do that here. We grind our cylinders to the same tolerance. From a private point of view, like a ready-mix producer, if it's his own data, he can use caps. When I was doing quality control at a precast plant, I set up their lab for them. I used those steel caps with the neoprene inserts because that data was just for our own design and our own mixes. That's the thing I'm referring to. So sometimes you'll see something that isn't quite what our procedures are, but it's going to be almost impossible to find something exactly the same unless we produce our own videos. I'm going to pull up a data sheet here for the compressive strength. I'll go over that and then flexural. Then we'll try the video here. So I'm going to do a share here. Okay, where am I here? Okay, this is the sheet now that you guys can all see this, I believe. Come on, why did you move over? It's not moving. Hold on a minute, guys. Having a problem here. Where am I here? Okay. Okay, this is the, you guys can all see this okay? Yeah. Okay, this is the form that you use for lab 4, and then the back part of it, or page 2, is what you're going to take your data and you're going to insert it in here. This is what you would have been filling out had you been physically doing a lab at Carsey. And you can see your group number, the date cast. Okay, I gave you that information. And you're going to record your diameter 1, diameter 2, average diameter, and cylinder area. And you're going to use this data, cylinder area, to calculate your compressive strength. Okay, because we know the compressive strength or stress is your load at failure divided by your cross-sectional area. And I would suggest you change this to newtons, okay, not kilonewtons. The reason why we have kilonewtons here is because the machine was reading in kilonewtons. But the reason, kilonewtons, newtons, same thing, as long as you know that. How do you determine megapascal? If you have a load in newtons and cross-sectional in area, okay, newtons per square millimeter, how do you get megapascal out of that? Anybody? Because remember, our strength is in megapascals. Anybody? You don't. Newtons per square millimeter is a megapascal. Right, exactly, Sean. You don't. Newtons per square millimeter, that's a megapascal. So that's why I'm saying is when we give the students the load in kilonewtons, they have to write this down in newtons, because then it's just direct MPa, okay? Before we do that, we'll go to what I've loaded up here. This is the data that I've uploaded into Learn for you guys. So whatever group number you are, 1A, 1B, whatever, okay? Looks like we're doing 2 7-day cylinders, and I just called them 1A1, 1A2. Call it what you want, but this is what most students do, because it's group 1A, cylinder 1, cylinder 2, cylinder 3, cylinder 4, and cylinder 5. So we used to make a set of 5 cylinders. The first 2 we would test at age 7 days. The other 3 cylinders would stay until we tested them at 28 days. And then 1A3, 1A4, 1A5, and so forth. And again, the diameters. Remember, and we're going to look at the CSA. When you determine the diameter of a cylinder, you measure it normal to each other. So in other words, perpendicular to each other. So you're going to measure it in the middle of the height, like in the middle of the specimen, and then you're going to go 90 degrees to it. So in other words, you're measuring it here, you're measuring it here, okay? So those are the 2 diameters, 100, 100.5. If you read the CSA specification procedures, you measure to the nearest 0.5 millimeter. Your area, okay? You're going to use the average diameter. Average diameter to determine your cross-sectional area. And you measure to the nearest 0.5 millimeter for your average diameter. If I'm going to be quite adamant now. If I see hundreds, I'm going to start deducting marks. Follow the procedures, okay? I've given you these. You'll notice that any of these dimensions are to the nearest half. Doesn't make any sense to measure to hundredths of a millimeter. Come on, that's the thickness of a hair. Doesn't make any sense, okay? So these are data that's given to you, and I've given you the load. This is the load of failure. So remember, load divided by the cross-sectional area gives you your stress, compressive strength. And to do that, okay, to do that, you want the average. So you're going to get a 1 cylinder break, another cylinder break, the average. A test, a compressive strength test, is the average of a minimum 2 cylinders, not 1. That's why those of you that have been involved in the industry and you're making a set of 3 cylinders, you usually test 1 at 7 days to give you an indication, and then the other 2 have to be tested at 28. I now prefer 3 cylinders at 28, because many times you'll see that 2 cylinders are going to break pretty close together, and sometimes 1 is off. So if it's an outlier, you still have 2 to average. If you make 2 cylinders, 1 breaks low, 1 breaks high, which is correct? Anybody? If for some reason you have a set of 2 cylinders and 1 cylinder breaks at 30 MPa and the other one breaks at 22 MPa, which one's correct? The middle? Okay, but now we're back to 2 cylinders. I'll get back to you with the 3, Fabian, but if you have 2 cylinders, 1 breaks low, 1 breaks high, which cylinder is correct? Because you can't average them. One's an outlier, obviously. You can't. Why would you take the low one?
The lower.
Why? Why would you take the lower? I'm not saying you're wrong. I just want to know why. To be safe. No, you're wrong there. Put it this way. Both those cylinders were made at the same time. More conservative? Well, they were made at the same time, same batch. Okay? Maybe something did happen physically to the one. But if one broke, high, where it was supposed to break. Not high, but it broke normal. That's what it is. There's nothing you can do to a concrete cylinder that's going to make it break higher. Once you cast a concrete cylinder, everything you do to it affects it in a way that it may take away strength. So if one cylinder made 30, there's no reason why the other one at 22 didn't make 30. So it's legit. So you take the 30. So that's where the 3 come into play. You got a 30 MPa, 32 MPa, and 22. Obviously, the 22 is the outlier. You can still average the minimum 2. A test is not a test unless it's the average of 2. So if you make 2 cylinders and one breaks low, one breaks high, you can't say that the concrete strength is 30. This is not the average. It's got to be the average of 2. And you can't say 30 and 22 and your average is 26. No, you can't do it. You got to say there's no test for that concrete. So when in doubt, make a set of 3. And I was surprised that that's what AMI does actually nowadays. Before they never did, but so maybe they're changing. Anyways, okay, so a test is the average of 2. And that's why you have 2 breaks at 7 and 3 at 28. Now, I had mentioned that many times specifications say to break 1, 7 and 2 28s, a set of 3. Why am I making a set of 2 for 7 days? Anybody? If you stop and think, an average, one breaks high, one breaks low, one's an outlier. You've got a 7-day that you're going to predict with the 28-day cylinder, with the 28-day strengths are going to make it. Whether you're going to be able to strip the forms, whether you're going to be able to open the traffic up for cars based on one 3-day or one 7-day cylinder. What happens if that 7-day cylinder, something happens to it? Just like at the 28-day, one's an anomaly. You get a cylinder that breaks at 20 MPa and you're saying, ooh, that's not going to make 28 days. We need 35 MPa at 20 days. That's no way it's going to increase that much from 22 or 20 MPa. Maybe that one 7-day cylinder, something happened to it. Now, if you had 2 7 days, same batch of concrete. One broke at 22, one broke again at 29, 30. If it made 30, there's no reason why the other one shouldn't. Now you can safely say, yeah, I think my strength at 28 days is okay. But to base it on 1 7-day, and yet you talk to a lot of clients and they say, no, we only want 1 7 and 2 28s. They don't want to pay for it. They don't understand, okay? So these spec writers, you look at any spec and you'll see that. I think even the City Winnipeg spec, if you look at that CW3310, one that we were looking at for the mix design, I think there they specify 1 7 and 2 28s, if I'm not mistaken. Anyhow, something to remember. So this is what you're going to fill out here for the 7-day cylinder strength. Okay. I've also done one here for flexure. Okay, we looked at compression. Now, typically we also make flexural beams, even though in industry right now we're strictly doing compression for the City of Winnipeg. There's a relationship between flexure and compression. So here you can see now it's calculated a little differently. When we get into the standard, you'll see why right away. You can see again a beam ID, and in this one I'm only doing 1 7-day beam instead of 2. Like we did the cylinders. Just typically you would do 2 7s, or you should, a set of 3 or a set of 2 beams. But for this virtual lab, I'm just teaching you the concepts of calculations that'll be adequate. What's a failure mode? Okay, we're going to look at the CSA specifications, and at the end of 9C, when we talk about compression strength tests, cylinders behave and fracture differently, okay? Depending on what mode of failure they're going into. There's some that are more conventional than others. And when cylinders do not meet their 28-day strength or their design strength, the failure mode should be noted. And we'll look at them here shortly when we get into the CSA standard. See, you can have conical bonds. You can have a failure that is a long plane shear, a short plane shear. You can have a splitting where the cylinder is failing almost vertically. Okay, and sometimes the way they fail could be due to a defect in the cap. If you're capping cylinders, instead of grinding them, you would be putting on a high strength capping compound to get the plainness. And this is something we're going to talk. When you're testing a concrete cylinder, the tops have to be plain. In other words, they have to be smooth. Okay? And when I'm talking smooth, you'll see the tolerances here right away. 0.025, 0.025 inches, which is 0.005 millimeters. Plain in any direction. 0.05, you say, in any direction with a feeler gauge. That's how flat they got to be, because you don't want to have any point loading. When that plate on the compression machine comes and sits on top of that cylinder to crush it, it's got to have total contact. There can't be any gaps or any high points, because then your cross-sectional area is not right. So these cylinders that you cast and you physically finish with just a trowel, they're not smooth enough. You got to physically put them in a machine and grind them or cap them, or use those steel caps that you'll see in the video that sits on top of the cylinder. And then that steel cap is where the plating of the compression machine forces it down. So we'll look at these fractures right away. Okay, that's the failure mode. It's nice to note, is it typical? Is it a conical bond or like an hourglass? And we'll have a look at them. Same with the beam here. With the beam is a little different because it's a prismatic. The beams are typically 500 millimeters by 150 by 150. But you're going to measure them exactly. And here I gave you those dimensions. And these are the dimensions that you would physically measure yourself had you had the lab. So you can see here, 155.9, 154.9, 155.1. Okay? And the flexural load in newtons. And you can see just by looking at these flexure strengths as compared to compression, they're quite a bit lower. Typically, flexure strength, okay, is about 1/10 that of compression. When you're talking megapascals. When you're talking imperial or PSI, it would be anywhere between, flexure would be anywhere between 7 to 8 times the square root of compression. But if you've got a cylinder that tests roughly at 44 MPa, your flex is going to be somewhere around 4, 4.2, 4.3, approximately 1/10. But because that's modulus of rupture, that's a bending, that's not compression. That's still, okay? When you're looking at a flexural load, it's a bending versus compression. Totally different calculations. We'll go through that, okay? So again, you'll just find your group, lab group, and then record this data, and then you're going to use that for your other form. Okay. Now, here it is. Here's the CSA standard 9C compression. 8C is the flexure. So we'll look at the compression. Again, I can't highlight anything here because they won't allow me to do it. They have it locked. You need a password of some kind. But anyhow, it talks about the machine. It talks about everything here. So the spherically seated upper bearing block and so forth. Okay. They talk about the diameter of the bearing face that's going to sit on the cylinder. What I essentially want to go through is, here's the capping equipment. We don't cap, okay? We grind our cylinder. So you take the cylinder, stick it in the machine, and using diamond grinding wheels, you grind that face on one end, you flip the cylinder over, you grind the bottom of that cylinder until it's smooth, such that you can then put it directly into the compression machine. Here they're talking about capping plates because it's still accepted. You can cap a cylinder with high strength sulfur capping compound. So they talk about the sulfur mortar. I used to cap cylinders before we ground. Sulfur, though, is very hazardous. It stinks. It's a fire hazard. I burnt my wrists one time because I was using hot molten sulfur. I was capping, putting it in the jig to get that nice round cap. It slipped on me, splash, sulfur went up, and burnt my wrist, and I couldn't get the sulfur off because it starts to cool right away. So as it's cooling, it's burning you, and then when it cools, you can then peel it off along with some skin. So sulfur isn't ideal. Plainness, okay? The cylinders have to be plain. They talk about the specifications for it. Perpendicularity. You can grind the cylinders smooth, plain, but they may be like that. So you got to be perpendicular. to the longitudinal axis. You got to test that. And you got to keep those records, because when a lab is CSA certified, CCIL, on behalf of CSA, checks all the records. Are those cylinders that you're testing, are you measuring them? Are you checking the plainness? Are you checking the perpendicularity? Are you checking the parallelism? Okay. And they talk about the strength and cap thicknesses if you're going to be capping cylinders. So there's a standard for everything here. Capping procedures, the capping compound. Is your capping compound strong enough? Because remember, you're putting a capping compound on top of a cylinder, and then you're loading it. If that capping material is weaker than the concrete, it's going to fail first. Your results aren't valid. Okay? How to place the specimen into it, and we'll look at the video here. Rate of loading. This is very important, guys, because I do ask a question on this on the quiz. You just don't put the cylinder in the machine and load it. Boom. Crank up the load and let it fail. You have to load it at a certain rate. The speed of loading is important, because if you load it too quickly, you're going to get a higher break. Okay, higher ultimate load, higher stress. If you load it very, very slow, it's going to break low. You're going to have a low strength. They're misleading, they're not accurate. So there is a certain rate that you have to do. And here you can see a loading rate, depending again whether you have a screw type machine or hydraulic. Okay, most of ours are hydraulic. So hydraulic operated machines, just think of a compression machine as just as a jack with a dial gauge on. That's all it is. You got to load them with between 0.15 MPa per second to 0.35 MPa per second. That's the rate of loading. Okay. Now, most people will say, well, what does that mean? Typically, wouldn't you load so many kilonewtons per second or newtons per second? MPa is a stress. There's a reason for it, because you never know, are you going to be testing a 100 millimeter diameter cylinder or a 150 millimeter diameter cylinder, or maybe a 75 millimeter cord that you took out of a concrete structure that you cored? Okay. If you had a load per second, which is one that you use for a small diameter cylinder, which one do you use for a large diameter? But a stress is a stress. Okay, megapascals is already load per cross-sectional area. So again, you got to do a back calculation. So that's why loading rates are given to you in stress per second, not load per second. But it's easier to figure out. So anyhow, so this tells you then that you're going to be loading it at the proper loading rate. Maximum load is the load that failure, when that cylinder cannot take any more load, peak load. Okay. Tolerances for testing ages. This is where the labs have to come into play. L over D, length to diameter ratio. Not usually important, because usually it's 2 to 1. But if somebody makes a bad cylinder and it tips over before it sets up, and you can't grind it, so you got to cut it off with a diamond saw and then grind it. So now instead of having a 200 millimeter high cylinder, you might have 170. The strengths are based on a ratio between diameter to length of 1.8 to 2. What the heck is it here? 1.8 and 1. Okay, so typically, if you're just grinding a cylinder, you don't have to cut it or anything. You're within that tolerance. You don't have to worry about the L over D ratio. If your L over D ratio is less than 1.8, then you got to put a correction factor onto your stress, MPa. Okay. Now, here's the reporting. This is the part that I wanted to get to, is because now you're going to be writing me a letter report. And again, like any other test, there's minimum information you have to provide. So this is the same in flexure. You're going to get a reporting section for the flexural strength. Specimen identification, number, or details. So a lot of this information is going to be given to me on your data, as a data. Some of it you'll add into your letter report. Okay. Minimum and maximum temperatures measured during initial curing. Well, that's not applicable to you. We don't have that, so don't worry about that. The date the specimen was tested. Well, I gave you a fictitious cast date, when the cylinders were made. 7-day test is 7 days from the day it was made. 28-day test is 28 days from the date it was made. Okay, so that again is, you'll notice that was on your spreadsheet, on that Lab 5 sheet that you're using, page 2 of the one you just did for Lab 4. Diameter and length if the L over D ratio is less than 1.8, more than 2.2. You'll notice you don't have to give me that because I believe the lengths I gave you are all between those. It's only if they're outside, because that's where then you would have to use a correction factor to your compressive strength. If you went back up here, where am I here? Okay. So you can see that there's a fair amount of information. Did I go past it? Anyhow, there's a if you test the cylinder and you had a ratio of 1. I don't know, let's say 1.7, then you would take the correction factor from the table and multiply it by the compressive strength, and that would give you your corrected compressive strength. Okay. I'm going through this maybe a little quickly, guys, but I want to make up some time here. Again, if you ever have any questions, let me know. So look at the reporting here. Okay. Now again, yeah. Now this is where the mode of failure. This tells you what your cap has to be. This is what the compression machine has to be like. Don't worry about this. You don't have to worry about the compression machine. But from a lab point of view, your equipment has to meet CSA standards. So you can see for this test, it just doesn't cover procedures. It covers equipment. Does your equipment meet the spec? This is a jig for making cubes for your high-strength capping compound. You have to test your capping compound. If you were capping your cylinders because you didn't have a grinder, you have to determine the strength of your capping compound has to be a certain minimum. Because again, you could be testing 44 MPa concrete. Most people grind now because for high-strength concrete, 40 MPAs are considered high-strength concrete now. 37 MPa is high-strength concrete. Most people just grind. If it's good for high-strength concrete, it's good for low-strength concrete. Here's the sketches of failure. For you guys, you know what? Because of the fact that we don't know, just put a type 1, okay? For all your criteria where it asks for fracture type, just say type 1. And here you can see if you loaded the cylinder, it would break. You would get fracture lines almost like this. The top here would come off, this one would come off. And it'd be almost like an hourglass. So these are called cones, cone failure, okay? Reasonably well-formed cones on both ends. Now, you shouldn't be going through the cap. You can, but you shouldn't. Sometimes this will happen if the cap or the cylinder isn't ground smooth enough. Typically, it's almost like a long plane shear, but two of them together, so it's like an hourglass, okay? Or conical bond. I refer to this as a conical bond. Here, type 2, you can see it's almost like a conical bond on the bottom end, but the upper part is going vertical, and it's cracking through the ends. This one here is quite common on very, very high-strength concrete as far as compression, because now it wants to behave in tension, okay? So it's developing tensile strengths or cracking. Another more typical one is this one here, long plane shear. Okay, it goes through most of the cylinder. It's almost like half of this one, see? So this is a long plane shear. You'll have short plane shears occurring here. But again, something breaking through the ends signifies that maybe you didn't have a very smooth surface. Maybe you had a high point. These have got to be ground very, very smooth. Rate of loading the same as shearing rate? Yes, I guess you can consider that because most of these cylinders will break in shear. The beams, though, sometimes will break in flexure. Some of them will break in shear, depending on the size of the beam. We're doing flexural because we're using 3-point loading, but the rate of loading is, yeah, it's the rate at which you're going to break that cylinder, apply the load to it. And then when you have something like this, where the tops just break, but the rest of the cylinder is intact, this is definitely something wrong with the cylinder. These are common. And these tell you that it's consistent, that the concrete's okay. So conical bond and long plane shear. For you guys, just call them all conical bond, okay? And again, typically that would be if your 28-day cylinder doesn't make strength. So from an independent testing point of view, if you're working for a lab, some of them don't report this, only when the cylinder does not meet the specified strength. Because now you're looking into it. What caused it? Could be Something like this tells you maybe there's prep procedure, casting procedure. Okay, so these are the sketches of types of fracture. Okay, now let's go up to the flexure, which is, where am I here? 8C. And I'm going to, again, go through it. You can read the thing. Now, flexural strength is known as modulus of rupture. Okay, R. You'll see the symbol R, modulus of rupture. And the formula for it, because you're going to have to calculate that, is the load P, load of failure, times L, okay, on the bottom here, times L, which is the span length, and we'll get into that, divided by B, which is the width, times the depth squared. And it tells you what each one is here, okay? R is flexural strength, or modulus of rupture. P is the maximum applied load indicated by the testing machine. That's in newtons. That's what you would read off the machine or what I gave you. Span length is the span between the supporting points of contact, which I'll show you on a sketch. B is the average width of the specimen, and D is the average depth of the specimen. Okay. Now, again, it's going to tell you what you have to report. Here's the setup that we would do. This is a flexural setup that you would see at car seat. Okay, you've got knife edges here, or supports. You slide the beam in, and the beam is long enough that you should have at least 25 millimeter overhang from the supporting rockers, and you're applying the load. Okay, it's only one load. So this is 3-point loading, believe it or not, but it's distributed, so the load comes through. So when you slide in, your span, L, is from the supporting points, okay, loading. And you divide it in 3, okay, L over 3, L over 3, L over 3. So span length is the length between the bottom supports, not the total length of the beam. Because Transport Canada used to make these beams almost twice as long. They would slide it in their machine, they would test that beam at 7 days, then it'd have so much overhang, they would take that and put it back into water, cure it for another 3 weeks, and then they would slide that in and do the 28 days. Okay? Whereas most people will have separate specimens per test. So it's the span length, is the distance between the supports, the load supports. Because as you're loading, you've got a support pushing up, you've got support pushing down. You remember your statics. Okay? So when you test this, it should fail within the middle third. Your beam's going to fracture. If it doesn't fail in the middle third, let's say it fails out here, then if the fracture occurs outside of the middle third of the span length by not more than 5% of the span, by not more than 5% of the span, the flexural strength shall be calculated as follows. Now, I didn't give you a distance A, but physically we had some beams that did not break in the middle third. So then the students had to make sure that they measured A. And what is A? Well, if you look at the bottom of that beam, that's where you measure it. You're going to measure the distance from the fracture to the closest support. A is the distance between the line of fracture and the nearest support measured along the center line of the bottom surface of the beam. Okay? A would be the distance between the line of fracture and the nearest support. So in other words, you know what L over 3 is because you know this distance. Divided by 3, you would measure the distance. And when these cylinders fracture, okay, when they break, then you can physically measure with calipers from where it breaks to this line. So when we slide this in a machine, it's easy. We take a felt marker and we make a mark here, we make a mark here, and we make a mark here, and we make a mark here. Because then as we're watching the machine, as the test is being carried out, we're watching it, and right away we'll see if it fractures, boom, right here, then we know, okay, we broke in the middle third. And sometimes it'll break nice, pretty vertical. Sometimes it may go something like this. I've had cylinders where it started to beams. It starts to fracture here in the middle third and then goes up to the outside. Okay. So we didn't go to that. I gave you a virtual lab where you don't have to worry about A. But actually, if this happened in a physical lab, you got to make sure that you comment that it break in the middle third. And again, for your lab, it asks you, did it break within the middle third? Just say yes. Okay. So you'll want to read this, the procedures again, reporting, certain criteria, identification. So your lab data sheet will answer a lot of these. Flexural strength calculated to linear is 0.1, not to 0.01. 0.1. I see so many times people giving me MPA to 3 decimal places. Okay? Not required. Carrying conditions are different from the standard. We'll say that they're within the standard. Defects, if any, in the specimen, if the average flexural strength is less than that specified. Well, really, we don't have a specified flexural strength. We have a compression. But this will give you an idea of at least a correlation between flex and compression. Hopefully, I've come up with a good enough ratio so it makes sense. I always try and give you results that are realistic. I will never give you a specific gravity of aggregate where you go through calculations and you get 1.6. It's not realistic. I wouldn't do that. So if you ever did a specific gravity test or you mass weight volume relationships with Natalie last year, if you had a specific gravity for clay soils in geotechnical materials 1 of 1.8 or 3.6, there's something wrong. You can't have that for clay. So then you would know you do something wrong. Same thing here, okay? I'm not going to give you anything that doesn't look realistic. Not intentionally anyways. I may do it by accident, okay? So read the procedures and let's quickly see if I can call up this video. I'll call it up now. Let me know as soon as we get into it whether it's tracking properly, okay? Because last time I had trouble, so I'm going to try doing it now here and we'll take it from there. Can you see this one? No, you can't see it. Okay, give me a minute here. Can you see it now? Yes, okay. I'm going to put it on. Once we start going through it, let me know whether it's working out okay or not. So I'll go to a full screen after once I know it's working okay. This is, I found one, and this one here is for the compressive strength. And they're saying with unbonded caps. You're going to see them using these steel caps with the neoprene inserts. And those neoprene inserts have a certain durometer number for flexibility. Because if you have a rough surface, the machine cap comes on top, forces it down, and then the neoprene fills in all the peaks and valleys. So now you're distributing your load evenly. Okay, let's try it. Let's see what happens. It's only 4.5 minutes. Can you hear it okay?
We don't hear anything.
You don't hear anything. Okay, hold on a minute. Thanks. There's a way of YouTube, sorry, not YouTube, WebEx here, there's a way of getting a sound. And I just see if I can find that. More. If any of you guys have an idea. Why isn't my sound coming up? Try that now. Can you hear it now?
No.
Okay. Sound is taken by WebEx. How come? How do I get that into so you guys can hear it? Okay, you know what? Can you guys hear me okay though?
Yeah.
Okay, I'm going to use the visual display on the bottom. I may stop the video from time to time and I'll ad lib a few things. So we're going to read the bottom here. If you can't hear the sound, at least read the bottom and then you can watch the video on your own. What I'm going to do here though is we'll look at the visual display on the bottom. And here you can see is what I was referring to is they're checking the smoothness. Now they're using, typically you would use a feeler gauge, almost the same that you would use when you're setting spark plug gaps in your car. Here he's using what's an Allen wrench, but it's obviously the proper diameter. So he's trying to check if it slides under that straight edge, which is machined, then he knows he's got a low spot. So you have to grind it. So he's checking these, and he's also going to check the perpendicularity to make sure that he's within 5 degrees of the vertical. So this is the important part, because when you load the machine, that knuckle that you saw, remember there was a little schematic of the platen and the compression machine? There was like a socket, like a knee socket. Well, the top platen of the compression machine can swivel a little bit. So if these cylinders are off just a wee bit, it'll conform to it, okay? So that's what that knuckle in the platen was, like a knee socket. But again, it's only got a certain amount of curvature or movement. So if this was way out to lunch, you would have to cut these cylinders and get them back to the proper dimensions. So let's work on the video caption here and then we'll take it from there. Here you can see he's doing both ends. So across the diameter, 100 millimeters, it's approximately 1 millimeter, okay? So obviously if he was off, it would send. So he's just using a straight edge, 90 degree, and determining it. So that would be 0.005 millimeters, I believe, 0.05. 25.4 times that 50, yeah. Okay. You can see here at the edges there, if you look underneath the straight edge, you can see that there is some gaps. But again, to me, that's a pretty thick shim. He's not thick, Allen key. It should be like filler gauges. There he's measuring the diameters, remember? Perpendicular to one another, mid-height. And you can see here that this is where the knuckle is, and you can see some springs here. So this upper platen, as it's called, has some flexibility. Okay, so you can follow the top of the cylinder. So in here, there's a knee socket, if you want to call it. And again, he's mixture. Now here, these are the end caps that he's using because they're not grinding. They're going to use end caps. Like I said, I used these when I was in the precast industry for our own benefits, but now CSA, as an independent lab, you can't use them. States, ASTM still allows them. There's the difference. These are neoprenes. They are a certain durometer number, and you'll use different ones if this is high strength concrete or normal strength concrete. Everybody can still hear me okay?
Yeah.
Good. Okay. So you can see now that these machine caps are going to be smooth, smooth, smooth. You want a longitudinal axis to go right through. So the distance here from there to the edge of the plate should almost be equal. You can see here, distance. You want to center it so the axial load goes right through the longitudinal. And see how it moves? Now, that is allowed. However, what's 10% of the maximum anticipated load? What's it going to fail at? Who knows? I don't know what the anticipated load is going to be. Is it going to be 230 newtons? Sorry, kilonewtons? So 10% of that. So most agencies, and when I was in the industry, I would not apply 10% of the anticipated load. I would make sure that my rate of speed is set with the selector here. Okay, we have it set based on the rate of loading for a 100 millimeter diameter cylinder. You know the rate of stress of loading. So we would have that predetermined and set so that we don't shock it, because I don't know what 10% of what. Okay, but if you knew that it was going to break at 250,000, let's say you had an idea, then you'd say, okay, I'm going to put 25,000 on right off the bat. And then from there, I'm going to make sure that my speed is set. Okay. When in doubt, play safe. Okay, that's PSI. We don't work in PSI, so that's where your MPA comes in our procedures for CSA. Okay. See, there's the ones we had in CSA. Eh? ASTM has the same ones. Okay, I should be able to find the other one I'm hoping here right away. Any questions on that? Let me just get another one here, guys. Where the heck am I here? I'm going to pull up the one for Flex now. If you guys give me a minute here. Where the heck am I here? Oh, here I am. Come on. Okay, this is the ones for the Flex. Okay, and again, sound, I'm going to have to try and figure out how to fix that. But okay, but we'll read the the video display or visual display. So this is flexural beam. Third point, and we're 150 by 150. Okay, the reason for that is obviously, you know, the surface of your beam mold when you cast it is going to be rough because you're going to put the concrete in it, you're going to screed it, you're going to use a float. But the other three sides have been formed against a steel mold. So again, just like with the cylinder, you're going to have a relatively plain bearing surface where your points of contact are going to be. So really, you cast the beam. In other words, D will now become B, and B will become D. So you're going to load it. This is the top of the beam, but you load it in the machine, smooth side at the top, smooth side on the bottom. And that's where your contacts are, okay? That's why he means turn it over. Now this is an 18-inch beam, so that gives you your overhang from your bottom supports. So there's your middle third, middle third. Yeah. Fortunately, this is imperial, but it gives you the idea. Again, these can swivel a little bit to take up the, where's my? Again, what's going to fail at? What's 3 to 6% of the maximum load? So typically we just ensure that it's in. You've got your rate of speed preset from previous ones on a beam. It may vary a little bit, so you make an adjustment as soon as you start loading. It doesn't take long to get that rate of speed. Plus that indicator, okay, your digital indicator gives you the rate of loading at all times. So you just turn your oil, it's based on oil pressure. You know, increase the oil, decrease the oil pressure, and that adjusts your speed of loading. These are just glorified hydraulic jacks with a dial gauge. That's all they are. See, we had to grind these. You would check, you know where your beam is going to have its contact. So even in the curing stages, you make a beam, you're going to test it at 14 days or 28 days flexural strength. You would grind ahead of time because it's easier to grind a green beam. When I mean green, when the concrete isn't quite set up, as 28 days later. We used to use cupstone grinders, and we would grind that concrete surface right where those beam supports are going. And that's the tolerances that you need. Now ours are metric, these are imperial. And if it wasn't, you would grind it until you would. And you would use again a straight edge with a feeler gauge to make sure, because again, if you don't have total levelness across those contacts, you got a high point. Your areas aren't the same. We basically shim it, and that's what they'll show here. You see now he's using a proper feeler gauge. So he's going to work all the way around on the contact blocks, eh? Okay. And there they're using leather shims because of the gap. And again, leather is like the durometer cap for the unbonded cylinders is going to distribute that load. Okay, and because they did have one where it had a gap that could go to the leather shims, they didn't have to grind it. We always put the leather caps in regardless, okay, like at car seat, because we don't go into grinding. From an independent lab, you have to. You gotta check, you gotta verify, you gotta record these tolerances. If you don't, CSA is gonna come and slap your wrists when they do a yearly check, because CSA certification really, really leans on record keeping too. You got to be able to show to the client. You got to be able to show to the standards that your cylinders or your testing procedures, your data keeping is within required standards and specifications. Okay, so they're going to put all the leather shims in there. And that's how it usually fails. And you can see right now, and he'll show better, it's within the middle third. Now, you don't measure the beam width and the beam depth before failure. You measure it at the fracture face. And here, this is the bottom of the beam at the top. It's a tension face, okay? It's just easier. So now he's measuring the width, okay? So you measure it along the fracture line. So it doesn't matter which beam you use, which half, okay? As long as you're measuring it along the fracture, because you know that these dimensions are going to change. They're not going to be exactly the same, and you're going to average all three. You do the same for D. So he's measuring it along the fracture face. Okay, I gave you a little bit of an insight to the test. Again, they're working in imperial, we're working in metric. So the CSA standard 8C, 9C is pretty specific as to what degree of accuracy you report, whether it's 0.1 of an MPa, if you're measuring to within half a millimeter of a diameter and so forth. So follow the standard, watch that video again with sound. The captions are pretty good displayed, so it gives you an idea of what the compression strength test is all about and the flexural strength test is about. I gave you the data, so again, you just use the data that you would have normally generated yourself. And for this one, just write me a letter report like we did with lab number 1. Make sure you cover the information that's required in the reporting. Some of them may not be applicable. If you have any questions as to not knowing what is applicable, what isn't, let me know. But again, keep in mind that your data will answer a lot of those questions. In your technical report, you basically want to state what standards you followed for which test. And again, I would suggest maybe, use subheadings. Talk about the compression strength test, summarize the data. You don't have to summarize, when you're summarizing data, it's the key data. Compressive strength at 7 days, at 28 days. I don't want to know diameters and everything else. That's in the attachment. And keep in mind, you don't have to type everything out. If you've got a printer, your data sheet, the one for lab 5, you can write that out in pencil. Okay, I gave you all the data on a spreadsheet. You don't have to take that form and retype it. You've got a blank form there, page 2, same form you use for lab 4. You can write out that data. That's typically what you would have in the lab anyways. If you were doing this lab in person at Carsey, you wouldn't be typing. You would be writing it as it's going on, because you would measure the cylinders before we loaded it into the machine. After we did the flexural strength test, I would take one half of that beam, I would put it on a table, your group would go over and you'd measure along the fracture line. And then you would record it right then and there in the lab on the pre-printed forms. So you don't have to retype everything. The letter, preferably, obviously typed and summarized with the attachments just included. And that can be the handwritten. Your data sheet typically goes into the file. You wouldn't give that to a client. You're going to give it to me because I want to see it, but you wouldn't give that to a client. You would summarize the compressive strength report is this, that. And typically, most agencies have a pre-printed concrete compressive strength report. Okay, it's not even a letter report. It's just a form with all that data that is needed: slump, air, temperature, when it was cast, what day, where the concrete went into the structure that the cylinders represent. So they know that this concrete went into the road slab between station 1+00 and 1+05 on the northbound lanes of Route 90. Okay, so in other words, they would know exactly where that concrete went into the structure that the cylinders are representative of. So they have pre-printed forms. And I believe CSA standard there in one of the appendix, you have access to it, actually gives you, and I don't know what appendix number it is, but they actually give you sort of a form, a pre-printed form that is used kind of in the industry. But everybody modifies their own. Okay, I had a different compressive strength report than what you see in the CSA. But CSA just gives you kind of an idea. So if you want, you can find that, have a look at it. Okay, I don't expect that. I'm not saying you have to do that. You're going to give me a letter report. You're not going to give me all that detail. You're going to give me what's required in the reporting for the flexure strength and for what's required for the compressive strength. Okay, you're not outcasting anything. Any questions? Okay, again, any questions, send me an email. And I won't just give you an answer right off the bat if I know that the answer is in there somewhere, but I will give it to you if it's something puzzling, okay? Like I say, I want to make sure you guys get in the habit of reading things and solving things on your own. But if you can't, definitely I'm here to help, okay? But give it a shot. And again, I'm stressing, talk to one another, please. If I'm getting a question from one individual in a lab group, that tells me then that nobody else in the lab group understands it. That tells me then that you've talked to everybody, right? If not, check with your members first, discuss it. And only then, if you can't figure it out, yes, by all means. But sometimes you're all working on it individually, which is good. That's the way you're going to learn. But if you're puzzled, check with your lab partner, check with the other lab partner. And if my notes aren't clear or my instructions aren't clear, yes, definitely get back to me. Okay? Any questions? This lab went a little longer probably than normal, so 3:40 already, but it's not too bad. Almost an hour. I hope I didn't take up too much of your time. Okay, if there's no other questions, have a good evening.